Thank you. Good morning. I'm Ioannis from Princeton. Today, I'm going to talk about Morpheus. This is a research project with Ioannis, Avramopoulos, and my advisor, Jennifer Rexford. And the reason I'm here is to get some feedback from the operators about how useful or how would you like to use this new mechanism to actually capitalize your path diversity to create a win-win situation too. On the one hand, you can hopefully get more revenue out of your current peering with your neighbors, and on the other hand, you offer better service to customers. Okay, we all know that large ISPs have rich path diversity, and hopefully there will be more peering sessions set up after this NANOC because you're all wearing the green dots. So first, from some measurement study, we know that top 2% of the large ISPs usually have 10 or more AS path for certain destination. And on the router level, the path diversity is even further, is even bigger. For example, I did some survey on NANOC mailing list almost a year ago, and some replies said it's very common to see 5 to 10 router level path. And the different paths actually have different qualities. Just two examples. One is security. There's almost more than 10 years ago, the AS7007 instance, your prefix can be hijacked. And in some other cases, you or your customer just want to avoid some downstream AS because of their lousy performance, for example. And in terms of performance, also it's a case. Some of our customers may want low latency path, but some of them may want high bandwidth. Different paths really differ in terms of performance. And given the kind of path diversity available in your ISPs, in your network, probably you can think about how to actually capitalize them in a better way. Today, we know that your customers may want different paths. So for example, financial companies, they heavily emphasize the security. And the VoIP companies, they want low latency. Content providers, they want high bandwidth. They want go closer to the eyeballs. And many others, they are perfectly happy with the default routes. So there's no one-size-fits-all solution. But today, unfortunately, this is the case. You choose the one quote-unquote best route and give it to everybody. So what we propose here is a routing control platform that enables ISPs to act alone, meaning that they don't need to collaborate with anybody else. They don't need to change their existing routers, but to capitalize their path diversity. So in the following of the talk, I'm going to cover two aspects of this idea. One is the kind of supports we need to make this work. It's all backward compatible. And the second is the design of the Morpheus server. It's a standalone server, a set of standalone servers that actually computes the route and push them to the routers. Okay, this is sort of a high-level view of the architecture. You have a set of Morpheus servers. They have eBGP session with your neighbors, and each of them only take care of a subset of your neighbors, but because they transfer the state, they communicate with each other. So each single Morpheus server will have the complete view of your BGP routes so that they can select the best out of all the routes for your edge routers and for your customers. It's worth mentioning that it is not the case today. So if you take a look, you will find different edge routers in your network will have different set of routes to choose from. So it's basically it's very possible none of your routers have the full picture of all the routes you learn from neighbors. And then, you know, after choosing the best routes, the Morpheus servers can push down the routes to your edge router through, say, IBGP sessions. And we propose to use IP or MPLS tunnels between every pair of edge routers, so that you don't need to worry the hot potato kind of stuff, because that can cause undesirable shift of traffic load once some route changes. Okay, so this is a kind of situation will happen if you use Morpheus. So even if your customer C1 and C2 are connected to the same edge router, they can actually reach the same destination through different paths, so that it gives you more flexibility to providing, you know, customized service to our customers. And the support are already there. You know, the VRF from Cisco and the virtual router from Juniper are readily available for to realize this kind of customization. And now I'm going to switch gear to talk about the design of the Morpheus server. To understand why we take the following approach, I'd like to point three limitations of the BGP design. The first is the overloading of BGP attributes. We all know that there are a lot of knobs to tweak, but actually they are not enough because you are overloading it. Okay, you tweak the local preference to support both BGP relationship and the traffic engineering. You know, you may get used to it because you do it every day, but actually it's quite messy. And it's difficult to add new policies because of that. For example, if you want to add security as a new policy objective to the whole route selection process, you're going to think about which knob should I use. The second limitation is the difficulty in incorporating SATA information. Let's take one step back and think about what would be an ideal way to select routes. You want to take you know, a lot of SATA information to help you with that process. For example, externally, you want to get some measurement data to tell you which path is actually better. It's closer to my customer, or does it have high bandwidth, for example. And you want to have, you know, business relationship, registry for previous ownership. All these kind of things, you know, it will help you to understand certain property of the path, either performance or security or so on and so forth. So today, it's quite hard to incorporate those information to your route selection process. Okay, so given the two limitations, what we propose is a different approach. Before the actual route selection process, we introduce a set of modules called classifiers. Each classifier does only one job. So one classifier will take a look at the route and say, okay, I'm going to tag this route learned from my customer with a numerical number. And for routes learned from my peer or provider, I'm going to tag it with different numbers. And another classifier who is taking care of performance, it will look at all the routes and say, okay, this route, according to my measurement infrastructure, it has the lowest latency, so I'm going to tag it with a number. So each classifier will only look at one property of the routes and tag it. Okay, it doesn't make any judgment, it doesn't make any rejection in terms of filtering. It will only tag a route and propagate all the routes to the decision process. And it's desirable because of the modular design, it's very easy to add new classifiers if you ever want to introduce a new policy objective in your decision process. And we also envision, you know, it's very likely different teams, even different vendors can come up with good modules so that actually they can evolve independently. In fact, there are a lot of nice algorithms coming up in the research community that can detect, say, previous hijacking in a very efficient way. So they can just contribute their code in some way, and wrap them into a module. Wrap them into a module. Then everybody can benefit from that. The third limitation BGP is it strictly rank one attribute over another. So there's no way you can make trade-offs between policy objectives. Here's an example. If all paths are somewhat unstable, then pick the most stable path of any length. It could be from a peer. But otherwise, pick the shortest path through a customer. It's a very reasonable trade-off between a business relationship and the stability, but it's kind of hard to do today. So what we propose to address this problem is to use a different way to pick the best routes. Instead of using the step-by-step ranking, we use a weighted sum. So don't be confused by these notations. Basically, the idea is now after the set of classifiers, each route will have a set of some metadata, right? They will have a tag for each policy objective. So you just specify a weight for each objective, then you compute a weighted sum. Whichever has the highest score will be the preferred route. And because your different customers may have different preference over the routes, so that translates into a different set of weights for the policy objectives. So in Morpheus, we support multiple decision processes. There's no reason you can't, especially given the advances of the multi-core, there's no reason you can't run multiple decision processes in parallel. Okay, so here decision process A may be set such that it always pick the shortest latency path, but decision process B, they may prefer the most secure path, for example, and you just set the weights differently, and then you can export the different routes to different customers according to their preferences, for example. We have a prototype implementation based on Zorp, and in that we implement several classifiers in a pipeline because that's sort of how Zorp implements its information flow, and we support multiple decision processes. We did some evaluation, and we found the classifier actually can work very efficiently. The most complicated one in which we implement a research proposal of identifying prefix hijacking, it takes only about 1/10 of a millisecond to classify a route. And then we look at the total decision time, which is, in Morpheus, it's just the computation time for a weighted sum, so it's very quick. When there were 20 routes per prefix, it's actually faster than the standard BGP decision process, because in that, at least in the implementation of Zorp, what it does is it will take a look at this prefix and go back to all the peers to see whether they have the route to the same prefix and retrieve that route and compare through the step-by-step process. That's actually much slower. And we set up an environment and evaluate its throughput. In this setup, we have 40 POPs, and one Morpheus server in each POP, and each Morpheus server maintains this many eBGP, iBGP sessions, and the sessions between the Morpheus servers, and we inject 20 routes per prefix. What we found is very promising because the x-axis is the number of decision processes running in parallel. The y-axis is the throughput of updates processed per second. So as we can see, the decrease is very slow, so that even if we are running 40 decision processes in parallel, we only get 1/8 of loss of the throughput. So it's pretty good. And I'm not saying you actually want to run 40 different decision processes, but the performance is there. And finally, I want to mention that there's no threat to stability, because for large ISPs, most of your customers are stubs. So even if you give them quote-unquote non-default routes, they are not going to propagate these routes to anybody else. They are just using them themselves, so there's no stability concerns. And actually, I'm not going to cover details here, but actually we also have a way for transit ASs to provide custom routes to their customers and without causing stability problems. If you want to know more about that, we can chat offline. Okay. In summary, Morpheus provides a simple, practical way for ISPs to capitalize their path diversity. It's significantly more flexible than what we have now. Introduce no impact on stability. It's efficient and scalable enough for even large ISPs, and it's backward compatible. So actually, as I mentioned, I have questions for you guys. What are your top policy objectives? And over the last 2 days, actually, I chat with some of you and got very nice feedback about your practical concerns. I'd like to learn more about that. And because the way you need to set the weights for the different policy objectives, you can actually give some of control to your customers if you want. So how much control you are willing to give your customers, or you are only willing to say, I have several choices for you to choose from, but anyway, I'm not going to let you touch my router. I'm going to just pick the routes for you, but I will let you choose which type of routes you want, and any other practical concerns. So very interested in feedbacks and collaborations, and here's the link to the technical report. Thank you.
Hi, can you go back to the graph you had at the beginning showing the multiple routes? The explanation for how you're choosing your routes is very well done.
Is it the slides?
The question I have is, how does R3 make a decision to route traffic from C1 or C2 differently? Because choosing your destination is one thing, but this seems to imply that you're choosing a path based on a source. And if you're using stock routers, how are you doing that without, redirection lists or some other technology?
Okay, so your question is, how does R3 know how to forward the traffic from C1 to C2 differently using existing technologies, right?
Exactly.
Okay, so it's a good question. Because we use tunnels, so that we can use tunnels, different tunnels for traffic from C1 to C2. And the other end of the tunnel could be the outgoing interface of R3 instead of the incoming interface of R3. So that you tunnel, actually, I forgot the exact term, but you can, in MPLS, you can tunnel to the outgoing interface. In fact, you can tunnel to the interface of R6 and R7, right? Then you can, right before the traffic leaves the outgoing interface from R3 to R6, you strip off the header. Then you know it's going that way. Ready?
Randy Bush, IJ. After some decades of getting resilience through distribution of the routing function over the topologic space, I wonder what happens when the central server fails. Do the routers recover and go back to normal?
Okay, so Randy's question is, what if one of the Morpheus server fails? Is that correct?
No, it was when, not what if.
When?
When it fails, yes. They will fail.
Okay, it's a good question. And it's not a new question, because it's just a new question. It's an old question asked in a new scenario. So I'm going to use an old answer for that. It's a typical distributed system. So conceptually, each Morpheus server will have a centralized, complete view of your routes. It's a desirable thing, what we wanted. But to avoid single point of failure, what we use is first, we use multiple Morpheus servers. And second, although it's too messy to show here, what actually probably going to happen is, each edge router will pair with 2 Morpheus servers. Okay, and that creates kind of redundancy already in place today. Your backbone router will pair, each of your, say, access router will pair with 2 of your backbone routers.
You're telling me why it won't fail. Everything we know that it won't fail has failed.
Yeah.
So what's going to happen when it fails?
Okay. So even if one of them fails, you can still get routes updates.
Sooner or later, more than one's going to fail. That's Randy's point. Everything fails eventually, and usually at awkward times.
Okay. Then, we all heard the previous talk. You can use the graceful restart.
Yes.
Remember what happened when AT&T put in one bad byte in all the 5 ESS switches, and all the switches went out on the East Coast?
The control plane fails, the brilliant engineers will try to bring them back as soon as possible. Meanwhile, the data plane can. Meanwhile, the data plane can still keep forwarding. And the point of multiple sessions is just the probability of 2 of them fail at the same time will be much lower than one of them fails. So even if one of them fails, it's not like life-threatening. You can still get the route updates from another server.
On the same slide, you mentioned about Morpheus connections between Morpheus servers to share the information. Is that proprietary, or how do you implement that? Is it like some sort of a BGP session between them?
It's definitely not proprietary. What we have in mind is something like add path. Okay, so you can send between Morpheus servers multiple routes for the same prefix. The most backward compatible way we are aware of doing that is using something like a BGP add path, the extension. All right. Thanks for your attention, and I'm happy to chat with you offline. Thank you.